In today's video, we're going to investigate the relationship between concentration and rate. As we've seen, lower concentrations of reactants mean slower rates. And so as the reaction proceeds and you use reactants up and the concentrations drop, well, that means that the rate of reaction is going to drop as well. If we look at this graph, we can clearly see what this looks like visually. Rate is the slope of the curve at any point. And at this point, where the concentration is relatively high early in the reaction, the slope is much steeper than at this point where the reaction has been going on for a while. So the question is there a predictable way to understand how that affects the rate? Well, let's imagine that you have a reactant A. We could define rate this way. The rate is equal to the change in the concentration of A divided by the change in time. This harkens back to what we saw in the last video, but we're going to use this notation to understand rate as we go along here. And it actually should be negative because this is a reactant, and so its concentration is going to be changing by decreasing as time goes on. Well, the law that we use to predict how the rate is going to change as the concentration changes is called the Differential Rate Law, or often it's just referred to as the rate law. It goes like this. Rate is going to be equal to a constant number times the concentration of A raised to some power. And I'm just going to call it M until we learn how to figure that out. Not all reactants are going to have the same M. You're going to only be able to determine what M is and what K is experimentally. So let's look at three cases. First of all, let's look at this. This is a chart that shows us the results of two experiments. In the first column, we have the initial concentration of A in moles per liter. Remember, it's a reactant. So this is the starting concentration. In the third column, we've got initial rate. That means what is the rate of loss of A, or the rate of production of product, in moles per liter per second. For two different experiments with two different starting concentrations, we experience two different rates. How can we build a rate law from this? Let's try it. Well, here I've reproduced this chart in a different workspace, and I want to start out by just redefining what the rate law is. Remember, rate is equal to a constant number times the concentration of A raised to some power M. And it's going to be our job here to figure out both what M and what K are. First, we'll work on M. I'm going to use experiment number 1 and just rewrite the rate law with real numbers. In experiment number 1, we see that 0.20 moles per liter second is equal to K times the concentration of A, which is 0.10 for experiment 1 moles per liter, raised to the M power. In experiment number 2, I see that I have 0.40 moles per liter second is equal to K times 0.20 moles per liter raised to the M power. I have two unknowns and two equations, so I should be able to figure this out. First, I'm going to solve for K, and I'm going to use experiment number 1 to evaluate for K. K is equal to 0.20 moles per liter second divided by 0.10 moles per liter raised to the M power. I've just taken this equation here and solved it for K. And now I'm going to substitute. I'm going to take the value of K that I just got here, and I'm going to plug it in for K in the other equation. So here's how that looks. 0.40 moles per liter second is equal to, now I'm substituting, 0.20 moles per liter second over 0.10 moles per liter to the M power. And then back to the original equation, this is multiplied by 0.20 moles per liter raised to the M power. Now I'm going to rearrange this equation a little bit. I'm going to divide both sides by the moles per liter second. Collect those terms. So 0.40 moles per liter second divided by 0.20 moles per liter second is equal to 0.20 moles per liter to the M divided by 0.10 moles per liter to the m. Now 0.4 divided by 0.2 is just 2, and the moles per liter second cancel as well. And 0.20 moles per liter divided by 0.10 moles per liter, they're both raised to the m power, so I could say that this is also 2 raised to the m. So now the question is, what is m if 2 raised to it is 2? Well, clearly m has to be equal to 1. So our rate law looks like this. Rate equals k times concentration of A to the 1 power. Now let's evaluate what k is. K, solving this equation for k, we find that k is equal to rate divided by concentration of A to the 1 power. So I'll plug in numbers. I can use either experiment. I'll just use experiment number 1. The rate for experiment number 1 was 0.20 moles per liter per second, and I'm dividing by concentration of A, which was 0.10 moles per liter. Moles per liter cancel out, and that leaves me with a unit of just 1 over seconds. 0.2 divided by 0.1 is 2, and so my answer is 2.0 per seconds. That's K. So I could plug this back in to the rate law and have a full rate law. Rate is equal to 2.0 per second times concentration of A to the first power. Here we have another experiment with different values. Again, we have the initial concentration of A and the initial rate, but the rates are not the same as we saw in the last experiment. Well, let's find a rate law for this reaction as well. Once again, we're going to start out with the basic definition of the rate law. Rate is equal to K times concentration of A raised to some power m. And again, our task is to find out what is m and then what is K. So using experiment number 1, I find that rate, 0.30 moles per liter second, is equal to K times 0.10 moles per liter raised to the m power. And for experiment number 2, I find that 1.20 moles per liter second is equal to K times 0.20 moles per liter raised to the m power. So just like we did before, we're going to evaluate K based on the first experiment. So K is going to be equal to 0.30 moles per liter second divided by 0.10 moles per liter, and that's raised to the m power. And now we're going to substitute that K into the other equation. So rewriting the equation for experiment number 2, 1.20 moles per liter second is equal to, substituting K now, 0.30 moles per liter second divided by 0.10 moles per liter raised to the m power times 0.20 moles per liter, again raised to the m power. And we'll follow the same strategy that we did before. I'll divide both sides by 0.30 moles per liter second, and I'll get on the right hand side 0.20 moles per liter divided by 0.10 moles per liter, and that's raised to the m power. Crunching this down, 1.2 divided by 3 is equal to 4. 0.2 divided by 0.1 is 2. So 4 is 2 raised to the m power. Clearly, it's easy to see, and without doing any fancy math, that m has got to be 2 here. Now that we know that, we can evaluate for K. Because we know that our rate law is equal to K times concentration of A squared. So that means K is equal to rate divided by concentration of A squared. So plugging in actual numbers from experiment number 1, the rate was 0.30 moles per liter second divided by our concentration. For experiment number 1, that was 0.10 moles per liter, but this has to be squared. Now, what happens to our units? I have moles per liter canceling out one time, but in the denominator I still have moles per liter. 0.3 divided by 0.1 is 3, and so K numerically is going to be equal to 3.0. The units that are left are per seconds divided by moles per liter. If you do all the unit arithmetic, that ends up being liters per mole per second. That's K. And then if we wanted a complete rate law again, we would plug that in for K. Let's look at this one. This is another example. 2 experiments done with the reactant A, and we have initial concentrations and initial rates for both experiments. Let's find out what the concentration dependency is for rate for this reaction. Following a similar pattern here, rate is equal to K times concentration of A to the M, and I want to find what M is. Using experiment number 1 as a starting point, my rate, 0.30 moles per liter second, is equal to K times concentration of A, 0.10 moles per liter, raised to the M power. Experiment number 2 says rate, which is 0.30 again, moles per liter second, is equal to K times concentration of A, which is 0.20 moles per liter, raised to the M power. What I'm doing here is I'm solving for K, so K is equal to 0.30 moles per liter second divided by 0.10 moles per liter raised to the M power. And now I'm going to take this value of K and substitute it into the other equation. So rewriting the experiment 2 equation, I get 0.30 moles per liter second equals, now I'm substituting K in, 0.30 moles per liter second divided by 0.10 moles per liter raised to the M power. And then that's times 0.20 moles per liter raised to the M power. So if I divide both sides by 0.30 moles per liter second, I end up with, on the right-hand side, 0.20 moles per liter divided by 0.10 moles per liter, both raised to the M power. 0.3 divided by 0.3 is 1, and 0.2 divided by 0.1 is 2. What number can I raise 2 to get 1? Well, anything raised to the 0 is 1, and so this is a reaction that doesn't depend at all on the concentration of A. Our next job is to evaluate for K. So we now know that rate is equal to K times A to the 0. But A to the 0 is just 1, so this means our rate is equal to K. So from experiment number 1, that means 0.30 moles per liter second is K. Now you actually don't have to do all that math in many cases to figure out the rate law. Like in this first experiment that we looked at initially, we saw the concentration double and we saw the rate also double. Since the rate law is basically saying rate is proportional to the concentration of A raised to some power, it doesn't really matter that there's a constant there. That's just a constant of proportionality that makes the proportionality an equation. What this is really saying is doubling rate happens when you double A, and so M has got to be equal to 1. Likewise, this second reaction here, we know that rate is proportional to the concentration of A raised to some power, and we see rate go from 0.3 to 1.2. That's a quadrupling. So 4 is proportional to a doubling, or 2 raised to some M power. What does M got to be? If doubling the concentration quadruples the rate, then the dependence has to be a square. And with this third one, we can see right away doubling the concentration has no effect at all on the rate. And so rate is just equal to K. Now one thing that we need to mention here is something called order. If m is equal to 0, we call that a zeroth order reaction. Just terminology that chemists use. If m is equal to 1, we call this a first order reaction. And first order reactions, you may have some familiarity from math classes with doing something with their kinetics. If m is equal to 2, of course, you probably figured out, we call this a second order reaction. Now, this all gets a little bit more complicated, but still manageable if we have a two-reactant system. So imagine we have two reactants, A and B. They react with each other to produce products. This is a chart that gives us the results of 5 different experiments. We have initial concentration of A, we have an initial concentration of B, and we have an initial rate for these experiments. Now, this is made easy by the fact that our concentration of B doesn't change for the first 3 experiments. And for the last 3 experiments, the concentration of A doesn't change. So we can look at one reactant at a time and figure out what the rate law is. And you can actually do this example fairly easily. Look at experiments 1 and 2. The concentration of A doubles and the concentration of B doesn't do anything. What happens to the rate? Well, the rate doubles as well. Well, if doubling the concentration causes a doubling in the rate, we've seen that it is first order in A. So we can begin building our rate law. Rate equals K times A to the 1 power. Let's look at the last 3 experiments. Nothing happens with A. Look at experiments 3 and 4. Concentration of B doubles. What happens to the rate? Well, the rate goes from 0.6 up to 2.4. If you divide 2.4 by 0.6, you see that that's 4. So doubling the concentration causes a quadrupling in the rate. So the rate depends on the square of the concentration change. So we can build onto our rate law and say rate is A to the 1 times K times B to the 2. So it's second order in B, first order in A, and then if we wanted to, we could evaluate for K. So I avoided doing all the math that I did with the single reactant examples. But I want to go back to this again and show you that without all of this information, I could still find a differential rate law given a much more limited set. Let's say I only had information for experiments 1, 2, and 4. So I don't have any of this information for experiment number 3. I don't have any of the information for experiment 5. Now, doing it the way that we did it before, you might say it's impossible to know what the order is in B because A never stands still. A is never constant for any 2 experiments. But that's not exactly true. Starting out from the assumption that it would be possible for you to figure out the concentration dependency on rate for A, or in other words, the order of A, we could write that rate is equal to K times concentration of A to the 1 power times concentration of B to the we don't know yet. Let's call it N. Now let's look at experiment number 1. From experiment number 1, we know that the rate, which is 0.20 moles per liter second, is equal to K times concentration of A, and we know that concentration of A is 0.10 moles per liter to the 1 power, times concentration of B, which we know is 0.10 also, moles per liter, raised to the we don't know what yet. So we can solve for K. We've done this in the past. K is equal to 0.20 moles per liter second divided by 0.10 moles per liter to the 1 power times 0.10 moles per liter to the N power. Now looking at experiment number 4, here's what we know. Rate, which is 2.40 moles per liter second, is equal to K times concentration of A to the 1 power, and for experiment number 4, that's 0.30 moles per liter, times concentration of B, 0.20 moles per liter, raised to the N power. And we're going to do that same thing where we substitute our K value from experiment number 1 into experiment number 4. So 2.40 moles per liter second is equal to, substituting now, 0.20 moles per liter second divided by 0.10 moles per liter to the 1 power times 0.10 moles per liter to the n power. Back to our original equation, times 0.20 moles per liter raised to the n power. Now let's kind of collect like terms here. 2.40 moles per liter second divided by 0.20 moles per liter second is equal to, sorry, I forgot something. This is also multiplied by 0.30 moles per liter to the 1 power. So that goes in here, 0.30 moles per liter to the 1 power times 0.20 moles per liter to the n power divided by 0.10 moles per liter to the 1 times 0.10 moles per liter to the n. So let's crunch all this down. Moles per liter second cancel out, moles per liter to the 1 cancel out, moles per liter to the n cancel out, and here's what we end up with. 2.4 divided by 2 is 12. 0.3 divided by 1 is 3. 0.2 divided by 0.1 is 2. So that means 12 is equal to 3 times 2 to the n power. So 12 divided by 3, which is 4, is equal to 2 to the n power. So n has got to be equal to 2. So it's second order in B. And then from here we could evaluate for K by just picking any of the three experiments and plugging in values and determining what K is with units. You'll have opportunities to practice this and you'll get hopefully pretty good at it. One last thing. The overall order of the reaction is the sum of the orders of the individual reactants that are in the reaction. So we found for this experiment that we're talking about in this example, rate was equal to K times A to the 1 times B concentration raised to the 2. So if you sum up these orders, 1 and 2, you find out that this is a third order reaction overall. So the overall order of the reaction is the sum of the orders of the individual reactants. Well, next time we're going to take a look at what's the effect of time on concentration. And for those of you who are in calculus, you'll get an opportunity to see a real-life practical use of what you've been learning in that class.